Hello, my name is Jose Michel Alba Rosales,
Hi, my name is James Melanyemi.
and this is Hailey's Hand version 3. It is a 3D printed prosthetic controlled using electromyography to simulate the hand of a 6-year-old.
The design philosophy behind Hailey's Hand 3.0 is to act as the golden mean between control and affordability. Furthermore, Hailey's Hand is designed to address an issue with childhood prosthetics. Namely, as the child grows out of their prosthetic, it needs to be replaced. And that could be prohibitively expensive for modest income families. Hailey's Hand is designed to be as inexpensive as possible while still being a quality prosthetic so that modest income family can simply replace it each year with a new, larger custom design.
This was designed in order to address the issue of children missing either their fingers or entire hand through injury, illness, or genetic disorder.
Hailey's Hand's mechanical operation functions on these few principles. When they receive instructions from the microcontroller, these micro stepper motors, shown here in the palm, turn, spooling a monofilament line that runs the length of each finger. When this line is spooled, it curls the finger, and that curl is resisted by these Ninjaflex elastic joints. The balance of force between the Ninjaflex and the spooling of the motor is what defines each state of each finger. Furthermore, each line runs from each motor up the finger, around a pin, back down to the palm, around another pin, and back up to the tip again. This allows the fingers to act like a pulley system. So essentially, the amount of force required to close this finger has been reduced to 1/3. And the only consequence of that is that it takes about 3 times as long to go ahead and close the finger. This this force multiplication was essential because it allowed us to buy motors that were much cheaper than would normally be required for this kind of task.
The electrical control for this design is composed of 2 parts: the motor control board and the myoelectric sensor. Muscle movement is detected through the electrical potential that the user gives off when intentionally moving their muscle groups. For this design, as you can see on the marks of my forearm, the electrical sensors are placed in these locations. Because of the dynamic nature of muscle movement, this microcontroller only sends a command when a minimum threshold is reached. Beyond that threshold, 3 modes of operation were programmed: pinch, clutch, and just hold. This in turn defines the general capability of our design.
As you can see here, the hand is perfectly capable of gripping. If you take a closer look at the thumb, you'll see that the thumb comes out of the side of the hand, turns at an angle, and terminates in 2 more joints. This is meant to replicate the function of a real-life thumb, namely this closure and this closure. In order to go ahead and have the control that approaches that of a real-life thumb, we found it imperative to have 2 motors for the thumb, one to operate this motion and the other to operate this motion.
This design does not include a battery. However, to operate it, it requires 5 volts and 2.5 amps.
With this design, we feel that we've achieved the objectives that we set out to complete. The hand functions. It opens, it closes, and all at the command of the microprocessor, which
is a human embedded control system design. It functions based on the thresholds sent via a myoelectric sensor. It functions on the ideas of computer logic, making it simple and easy to use for a child to operate.